So this today is the last day of our course, so we will finish today the discussion. But as I said, I can help you with discussion that we had in these classes with another more in your research point of view. Just to let know, so last class we talked regarding interfaces. Then I comprised these three in this class today because I didn't finish with the flexible organic devices. So I will start with this one. Then I'll go with stability and talk about characterization. I will try to do it quickly to show, but you can see in the YouTube if it's not a problem to see later. So the main advantage of using organics are the flexibility. So I think if you want to choose one substrate to apply organic materials, you can choose flexible ones, no matter what kind of, if it's transparent, depending of the application. But I think I must be here because of the camera. But the flexibility of organics, it allows to apply for several kind of applications, and also because because of my husband just grab the cell phone. Because yes, he is in the MIR. So the Maison, we are living here in the Maison International of the Research. So I just grabbed his cell phone and he forgot with me.
But he came here with you from the beginning, like, or he just visit you, or he came here with you?
He came.
Came with you?
Oh, no. So it's a long time. He can work online, so he can do it. So just to continue, so we can apply the organics for flexibility devices. So in this way, comparing with inorganic, that is more rigid, the organic, they can be more thin, they can also be more stretchable, so we can apply it on substrates that are flexible. In terms of it, we have these pictures that simplify some application of flexible electronics. So we can apply for healthy application, for instance, applying in visual sensors, pressure sensors, strains, also some wearable gloves, wearable watches, wearable shoes, and also several kind of sensors. And to feel the sensors, we must, for instance, use several kind of electronics, but one battery needs to fill the sensor. But to fill the battery, we must use one solar energy to convert solar light into electricity, or also indoor light into electricity. So we must have this kind of system, and this is the most advantage to use organics and also perovskite, because we can apply it on a substrate that could be more flexible. I have this problem. And why the organics are ideal for this application? Because comparing with organics, and also the hybrids with perovskites, they can be low temperature processing. So these are enabled to apply with deposition in large area. For instance, here we can see a picture of a roll-to-roll machine with slot die coating. So we can use this low temperature to process films through solution. So solution processable films allows to do this printing in large area with different techniques. So this one is one example, but I'll talk more about different techniques also. And the organic, they can be applied because of this processing being low temperature, solution processable, and also because of the mechanical flexibility. So we can apply organic materials and hybrids on substrates like PET, PEN, polyimide, and these substrates and also the layers that goes up the substrate will have a mechanical strain that is related with the radius. If we have these smaller radius of stress, we can assure that they have a higher strain, and thicker devices usually have this more strain because they are more rigid. And so if we can minimize the thickness, we can minimize the strain. So the organics has this high coefficient through absorption and also mobility with the low thickness. So this it's one of the advantage because we can apply it with flexible substrates, and also because of that disordering that we talk about a lot on this course, this disorder or amorphous morphology, they can allow this mechanical strain be suppressed with this stress. So we can have more flexibility with the substrate without any significant damage. So if you think on inorganic, for example, you have a too rigid system, and if you think organic, you can have this flexibility with the material. But we have some limitations as we are dealing with materials. We can have this failure on mechanics coming from the cracking of electrodes, for instance. Also the lamination, because when we increase the stability, we apply lamination. So in terms of long time of stress, we can have this delamination coming from the mechanical stress or temperature stress. And also the organic has this plastic deformation that comes from the more flexibility with the temperature. So depending of the application, also you have different stabilities, as we will discuss later, but in terms of mechanical flexibility, the organics are the most important material. Regarding the application of electronic devices with flexibility, the limitations that we have when we use organics as semiconductor or interlayers, or we have these electrode limitations. because we usually use, for instance, ITO as electrode. So ITO, we have this high conductivity, transparency, but also they are very brittle. So if you want to apply, for instance, in that row-to-row machine, the ITO, it's not suitable. So we must just switch for another oxide, even though we use a semiconductor based on organic materials. The electrodes and transparent electrode, they have this limitation. So if you have flexibility on semiconductor and don't have on the metal or the electrode, doesn't matter if the organic are flexible. So we must seek new materials to replace, for instance, in solar cells, the ITO, both for organics and perovskites also have this limitation because of this critical flexibility of the ITO. So in terms of new materials for flexibles electronics, we have this nano, I forgot in English, silver nanoids, because come from the Portuguese term. So we can replace with this silver nanowires. It's metal, but if we reduce the thickness, we can increase the flexibility. We can also use carbon nanotubes, doped or synthesized with polymers. There is several research on this topic to seek new materials for electrodes. Also the graphene, but graphene has limitation. For instance, in large area, we have this kind of issue related with morphology of graphene. And the most, I think nowadays, most studied for application are the conductivity polymers, mainly P-dot-based polymers as electrodes for solar cells and also for sensors, for several kind of electronics that are flexible. Just to see here the relationship of electrodes and the mechanical electrocoupling. So we have this mobility related with the mechanical strain. So if we increase the mobility, increase the strain, we will reduce the mobility of the electrode. So seek new electrode that could have this non-stressability related to mobility. It's better for the application. Also, the electrodes has this damage on the morphology that usually reduce the conductivity. So sometimes the stability of devices goes down, but it's because of the cracks of electrode and not because of the organic compounds itself. In terms of organic photovoltaics, we have, as I said, this possibility to process the devices with several techniques, because each technique here that I will say are solution processed. So we come from one ink and we deposit with different techniques. So the techniques are blade coating, slot die coating, inkjet printing. These three that I highlighted here are the main seek through large area application. Even though we use, for instance, spin coat technique. Spin coat, we can just deposit in small areas, so the spin coat is not suitable for large area application. So we must just switch to spin coat to meniscal guided technique. And when we do this, switching from these two techniques, the materials, they behave completely different because of the dynamic of film formation. So if you are, for instance, you are working with self-assembled monolayers, you deposit with spin, try to do the same devices with blade, and see the color relationship with the spin and blade. You can see that with the blade coating or meniscus, or another meniscal guided coating, they have more issues that when we work on spin, we don't care because, for instance, with meniscal, it's hard to get thin layers, and sometimes material that you want needs a really thin layer. So you must to deal with the concentration, also the temperature of process, that sometimes in the spin we do not have these questions because the spin is quite easily to process thin layers. So in terms of large area challenge that we could focus on discussing because of the transfer from lab scale to large area scale are the thickness uniformity. So sometimes uniformity is not so well because of the system of the position. The meniscal guided system are quite challenging this way. But if you have one material that has more uniformity around and the thickness uniformity around all the substrate, you have better material than some material, even though has higher efficiency, but the uniformity is not well, it's not so desirable. Also, in terms of large area, we have challenges on defects because when we process in large area, usually we process in air condition. So we do not have a huge nitrogen glove box with a roll-to-roll machine. So sometimes we have these defects coming from the oxygen. So materials that has more stability with oxygen also are more desirable. And the reproducibility that is an issue with the organic materials. In terms of the position, I put here, for example, one overview of the slot die coating. So meniscal coating is this, it's quite a hard the picture, but it's this this wet film here formed over the substrate, and the movement of the interaction between the blade here and the substrate created one meniscule that you can spread over the substrate. You can fill this slot die, you can fill solution in this head here and deposit it over the substrate. And then in terms of roll-to-roll, these deposition are scalable because usually you are using substrate that are flexible, so they needed to roll in the end, the substrate, and the meniscus, it's coated near to one roll to increase the wettability and also the deposition. So in this way, we can deposit here and the row in the end of the deposition. So for instance, if you have several layers, you must deposit each layer with this technique, and then you can have a system that with several setups of deposition. In terms of flexibility, one issue also to prevent degradation that is very important for organics and also perovskite is the encapsulation. So encapsulation, it's a huge issue to avoid oxygen degradation and also moisture ingress. So we know that oxygen and water can induce some damage in the stability of materials that we use. Perovskite organics, they can reduce the band gap or also increase the resistance of the materials. So encapsulation is one strategy to avoid the interaction of the material with the oxygen and also with the water. So if you see here, this example, it's one electrode. It's one device here that has glass, ITO, organic layer cathode. So we usually put some one adhesive that can be epoxy based or acrylic based adhesive, and also put over the device glass or another plastic. If you want flexibility, you must put another plastic with better flexibility, but with lower oxygen intake and also lower moisture ingress. So if you put more layers on your devices, the flexibility reduces because you have more thickness, thicker device. So it's also a trade-off in terms of new substrate apply as barrier in encapsulation that could have more flexibility, also could have more blocking more oxygen and more water. So sometimes just coating, for instance, one material over the barrier and put over the device, it's enough to block more the oxygen intake. So there is several strategies to increase to reduce the oxygen degradation and also the water intake, and not lose the flexibility of devices. So here I just put because of the example. If we have laminated devices, and we sometimes, because of the application of the device, we bend, we can have this failure on the lamination, and also this will increase the moisture absorption, so it will decrease the stability because of this failure. In terms of flexibility, what we can think regarding of interface materials, ADTL or ETL. Here I just put one example of P.PSS that it's most used material for interfaces. We must deal in the interfaces the adhesion because you remember that we have this dipole formation on the interface. So sometimes if the material is not adhered over your semiconductor or over your another layer, you have these adhesion problems because of the delamination of the layers over the semiconductors. So, for instance, the P-dot PSS that are more the most studied material for electronics, they have this issue related to delamination. So the PSS that has this isolator properties, they can also act as to reduce the adhesion between the layers. So it's quite easy to delaminate your interface with P-dot PSS. So replacement of P-dot PSS as interlayer or as electrode also it's one of the issues nowadays because we must deal with this delamination. But sometimes we don't find any solution processable material with efficiency so high as P-dot PSS, then we must somehow deal with the same material but with different strategies. For instance, put some additive or cross-linking to increase this adhesion between the layer. So here I just put one example. I didn't put even the reference, I forgot. But you can see that the P-dot PSS, he shift between the time and the morphology of the material, it's quite different over the time. So seek new materials also with the more flexible, but without some large area issues. It's better for our applications. So just to give overview on this flexible devices, there is a multi-physics perspective. So if you see one layer, you can think on the physics behind this layer, but you can also think on the processability on large area. What is the most important thing related to the large area deposition. So sometimes we cannot, we are too far from the challenges coming from the large area and just focus on the academic point of view, but in terms of appliement of the electronic, it needs to overcome these issues. So the electronic transport is an issue on the flexibility because of the mechanical deformation, and also the flexibility comes with the environmental exposure. So usually we cannot work with the nitrogen or controlled deposition. Then we must deal with this environmental issues. But the application is quite clear and is quite important nowadays because of these health integrated systems, and also because of the application, for instance, is some architecture that needs low weight of devices. So to the second talk, this class today, I will divide in 3 parts. So the second part of this class will be more in terms of stability. So the stability, as I said, it's quite important because when we go to the large area deposition and also the application of the devices, no matter what kind of devices, if it's transistors, solar cells, or batteries, capacitors, or sensors using organic materials, we must deal with these stability issues. So to overcome the challenges of the large area deposition, or also to improve the stability of some specific application. So organic devices, they have this metastable system because of this amorphous morphology. So they have the nice characteristics because of the flexibility and also the low energy consumption due to these amorphous structures of the material. But when we analyze in terms of stability and comparing with the inorganic, we have this more unstable system than some specific inorganics. So in terms of performance of stability and performance related with the stability or performance analyzed over the time, we have this chemical instability. So sometimes the organic materials that we are working has this catalytic property to work with some with the water or with oxygen, so it's easy to break some specific bond of the structure and do the bond with oxygen, and we have this chemical instabilities being the hardest thing to deal. But seek for new materials that has alkyl chains, more stable, or core chain or core of the material more stable also. It's important to overcome this instability coming from the chemical side. Another thing that we work a lot on organics are this morphological evolution. As I talked, the organic, they don't transport through electrons and holes, but they have this polarons. So there is a relationship with the charge and the morphology of the material quite tight. So when they are in the non-equilibrium condition, we can have this morphological evolution even though there is not external stress, for instance, with temperature, but just with absorption of the light, we have this morphological evolution of the compounds. So this is the morphology, and the morphology of the organics are important because we must to suppress this segregation of materials that we have mixed inside of the film. So sometimes the stability is just to freeze the morphology that we have with the high efficiency, but it's hard because over the time we have several turn on, turn off light intakes in the solar cell devices, for instance, and this switch the equilibrium of the organics. And also, as we discussed, the interface degradation. So during the operation of the device, there is usually charge accumulation in the interface. So if the charge is accumulated in one interface and is not accumulating in another interface, so we have this gradient inside of the device, and this gradient of charge can induce a degradation because of the morphology, changes on the morphology through charge accumulation, or also charge trapping between the interface, or the delamination, as I said earlier, regarding the interfaces of the several layers. In terms of stability, we have these key metrics, as we call T80 and T50 lifetime. So it's the time that we reached 8% or 50% of the efficiency in terms of the begin. So if we have, for instance, normalized PC, the 8% in this orange curve here, it's here, the timing of this one. And 50, it's more longer. It's longer, but it will be fifth, the time to reduce 50% of the efficiency. And in terms of solar cells, we have these two kind of measurements also for OLED. It's quite important to see the efficiency of the time, because in organic we have these two different degradation. The first one, I will not talk too deep on this, but there is exponential degradation in the beginning that is usually with T8 lifetime, and then another degradation, it's more planar degradation. So we have these two fitted curves inside of lifetime. So these two degradation, we can think regarding the physics behind the degradation is different if you have the higher degradation here and low degradation here, then low degradation here and high here. So there is different problems coming from these two different time of the stability. So it's quite important to evaluate the efficiency of the materials of the device over the time, so we can see how it changes and how is the decayment of the efficiency, or if we are dealing with the operational or self-stability issues. So here just one example with this work, they just put 130 materials, so a ternary blend, for instance, in organic solar cells, increased quite increased the stability, quite a high stability than without this ternary composition. And this is important because you can see that is the same materials, and just the mixture between them that can be related because of the morphology, or there is some protection from one material to another. So in terms of performance, I just put here the perovskite also. It's quite important to deal with the UV exposure. So in terms of stability, the stress that comes to degrade the devices are through UV light. the chemical stability of the composition, the moisture or oxygen intake, the thermal instability, the structural transformation or morphology change, and sealing issues. So if you want to increase the stability, you can attach one of these things, and if you attach the 6 of them, so it's quite nice to the development of the device. Sorry. So in terms of degradation, what we must deal is generally with these factors that I exhibit. But if you think on applications, for instance, you have different regions of the world with different solar spectrum, with different humidity, with different also, for instance, if you apply your material near to the beach, you have more salinic. Are you planning to? Okay. If you have a more close to the beach, you have water with salinic. Because of the sea, and so the stability is quite important to investigate directly with the application. Also, there is some protocols that we have that I didn't put here, but will be on late. But there is some protocols just to compare the materials that we must follow, because sometimes you want to evaluate if your material is more stable or not. So you must follow the ISOs, that is the protocol testing, to see if the stability is. Huh?
We stay from 5 minutes.
Okay. The ISOs give us some rules to just compare the materials, but we can. It's better to apply directly with the application and see the degradation coming with this directly related to the application. So in terms of degradation, there is intrinsic degradation, molecular instability, or external-induced reactions in general. So the extrinsic degradation comes from the oxygen, moisture, and UV radiation that I said. This one we can deal with the insulator properties. So we must apply the lamination of the device to overcome the stress coming from the water, oxygen, or light. So improve the barrier, you can improve the stability, but there is some things related with the intrinsic that comes from the device itself. So this is the example. For instance, one solar cells using zinc oxide. Zinc oxide, they have this property, catalytic property. So it already observed that zinc can increase the degradation because of the catalytic property of oxygen inside of organics. So depending of the application, is not so desirable, even though the zinc oxide, it's quite important material as ETL. And also, just to see that that's not just intrinsic degradation related to the materials, but also has some degradations of the devices related to the operational degradation. So, for instance, electric field. If you have electric field here, and also with application, sometimes we have different stress coming from the electricity issue. So there is charge accumulation and also chill heating because of the contacts with the converter or the batteries that we use it, or the contacts between the cells itself. So in terms of intrinsic degradation, we see that is quite related with the excited states. So if you have, for instance, here I just put a singlet, but you can have if you have different materials and you have this mixture between the materials, you have materials with several landscape inside of the device. So this difference in the energy, sometimes we lose, and these losses, we can increase the instability of the devices. So overcome these excited status losses of solar cells, for instance, it's quite important. The charge transfer state that we have here, that is the state between the two donor and acceptor materials. They also can act as reaction system to degradation because of the property to increase the morphology of the change of morphology, and also the reactivity with the oxygen. So the excited states, they have this very reactive system, so they interact with the oxygen quite easily. The charge induced also chemical changes because of the potential ox-redox properties of the materials. So sometimes the charge you just want to collect, but you can induce some chemical changes also. And the traps also can improve the degradation because of the charge accumulation and the Joule process. So the degradation is not just chemistry. We not overcome the degradation just doing new synthesis. We can overcome this degradation using physics, but understand the excited state and how the morphology or the reaction of the excited state with the material that you are using, you can increase or decrease the stability. So in terms of trigger, the extons and the free charges, they are these species that trigger reactions or morphological reactions or chemical reactions also. The oxygen-induced degradation of organics, it's usually happen with some degradation with one component that has in the molecule or polymer. It usually happens with this superoxide interaction with the oxygen with the electron, and this superoxide attacks with, for instance, the conjugated backbone. And this degradation, we can break the chain, we can reduce the mobility, and also changes in the electronic properties of the material. So sometimes you see changes in the band gap. It's because of the reaction, degradation induced with oxygen, and you do not see because sometimes it not happen with with some material. So depending of the kind of the radical that you have, you can also have different interactions with the oxygen and also with the water in terms of the chemical changes. Sorry. That's not a problem. Have a good meeting.
So that is serious meeting.
Yeah, it's a serious meeting. It's all right. And because you have this break in the schedule in the academic, so it's better to have this meeting.
Yeah, it's coming soon, so yeah.
Yeah. Goodbye. See you later. Tomorrow on around the office.
Bye.
Bye bye.
Have a good day.
You too. Bonne journée. Oi, João, você consegue me ouvir?
Oi, Lu, consigo.
The moisture also can impact in terms of degradation. It usually interacts with the electrodes. So the aluminum, for instance, they can degrade because of the interaction with the moisture. Also, the silver can interact with the moisture. So it usually happens with the electrodes because of the electrodes are usually the first material to meet with the moisture, so it impacts directly with the electrodes. It causes delamination also because of the moisture intake. For instance, the PSS, the PSS are soluble in water. So usually when moisture comes, the PSS delaminate the interface because of the solubility of PSS with the water. The interface degradation because of the moisture. So the water induces this charging trap in the interface. And also it can cause some electrical shorts because of the water intake. The photooxidation is another issue related to the stability. When the light together with the oxygen, they created this reactive oxygen species. So there is one singlet oxygen formation, and this gives some radical reactions. It usually affect the donor polymers and also the receptor because of the semiconductor properties. And the Y6 family, for instance, it's nowadays the one of the most efficient material for solar cells, organic solar cells, but in terms of the stability, it's quite issue with the photooxidation stability. Here I just put one example with the photochemical process being related with the intake of oxygen and also with the light. So you can see that has some morphological changes, but also you can have some changes in the chemical structure of the material. Another stress that comes from the degradation is thermal degradation. Sometimes we don't discuss too much about thermal stability, but it's quite important, the thermal stability for organics or other hybrid materials. Because when we apply, for instance, solar cells outside in outdoor condition, we have, using that ISO's protocol, the thermal stress around 6 degrees Celsius. So the stability around with this temperature is quite important to analyze. If you have a higher temperature, you can also analyze it in terms of sometimes the application of the device will be on specific architecture that has some temperature higher than 6 degrees. So 60 degrees, the medium of the test, but sometimes we'll have more stress or sometimes we have lower temperature. So investigate the material in terms of thermal stability is also an important thing to deal. The stability, thermal stability can increase the phase segregation. So for instance, if you are analyzing the active layer of the devices, you have this well-miscibility between the materials, the donor and acceptor, to increase the extone dissociation. And if you have this phase segregation, you will just reduce the separation between the materials, and this segregation will reduce the extone dissociation, and this directly impact the stability of the film. So this is quite critical for the active layer of the organic photovoltaics. The nanoscale phase separation over the time. So this has this concerning around the domain, the reduced interface between donor and acceptor, and consequently reducement in the charge dissociation, and also increasing the recombination because of the morphological changes coming from the thermal stress. The interface degradation that we discussed here, it's usually the delamination that we discussed, but also has this dipole arrangement. Depending of the material that you have, you can have these chemical reactions, and also the metal diffusion inside of the active layer or the interlayers. So for instance, here, the P.PSS doped, because of the dipole formation, the ions will migrate through from the Wouk to the interface. So there is some accumulation of the ions here that can impact on the performance of the device. Also, another important aspect to study are the excited state, as I discussed. For organics, the electronic properties directly impact the stability of the material. So in terms of the electronic properties, we have this spin-related electronic properties of the organics. We probed that has some triplet related to the organic materials. So even though it's not so easy to access, they are there. So it's important to mention that the singlet and triplet states, they have different lifetime. So the singlet usually peak seconds or nanoseconds, and triplet are milliseconds or seconds, depending of the material. And this triplet and spin orbit coupling, it can react with the oxygen quite easily. So in terms of stability, the relationship between triplet of organic materials and the stability, it's quite important to discuss, because there is some ways to overcome these states, and also to improve the stability of these new molecules that are in the literature. So the triplet degradations usually comes from the singlet transition from the grounded state, singlet state, to excited state. The internal cross-section with the spin orbital coupling between the states. So there is some swift between the spin to move the electron to the triplet state. This triplet state has longer lifetime. So in this way, they can interact with the oxygen, causing some singlet oxygen, or also induces some oxygen radical, which are very oxidative burst. So in this way, how we can assess this triplet, or how we can overcome this triplet, is also one issue to do. The electrical stress that we discussed is not just regarding the organic, but also every electronic devices. Here put on one example of the perovskite. Here is one example of the organics. So the high bias, in terms of application, we can do charge accumulation, induce also trap formation. This increasement on the trap or the charge accumulation can increase the recombination. And also in terms of organic, for instance, if you have pristine material here, and also you have one degraded material, you can break this chain, not just with electrical degradation, but also with light degradation. So there is some radical reaction that could increase even more the degradation. And in this way, for perovskite, that I just put one example here, we have this free ions movement inside the layer of the perovskite. So in terms of when we apply voltage, we have this movement coming forward and reverse. This is the reason, mainly the reason for the high hysteresis of the perovskite, because when we do a forward and reverse bias, we have different performance of the photovoltaic device, and this is because of charge accumulation on the interface. So these free charges here, they can easily accumulate on the interface, depending of the organic or inorganic interlayer. As the girls are working with the self-assembled monolayers that are dipole formation, this is quite important to deal, because if you think that the dipole has one polarization here, it will attach the ion just in one side. So to overcome these high hysteresis, it's quite important to improve the performance of perovskite. So in terms of map, to do a map of degradation, we must deal with external degradations that induce charge or trap, that could induce chemical reactions and also morphological changes that this can reduce the device failure and improve the device failure. So in terms of stability, intrinsic stability, it's E. In terms of extrinsic stability, we can deal with the encapsulation of the devices and overcome the outside stress inside of the organic device stack. So just to give an overview on the encapsulation strategies. The encapsulation strategies, we can deal putting that barrier. So just come here, the barrier, as I said, sometimes it's the material that will barrier the oxygen or water intake in the device. So in terms of, for example, organics or perovskite solar cells, we have this structure, ITO, ADTL or ETL, organic or perovskite, ETL or ADTL, depending of the device architecture, and metal cathode. So to overcome the degradation, usually puts encapsulation over the device and under, because we can glue both of them. And to glue them, we use adhesive. So the adhesive is also important because some adhesive can interact with the materials here, and it's not nice if they interact, because they will induce some charge trapping or degradation intrinsically, but related with the chemical reaction between the layers of the device with the encapsulation process. So the barrier layers, they can be glass if you are working with rigid devices. They can be polymers if they are flexible. The polymers, they have different kind of polymers to work as barrier. And also there is some multi-layer barriers, because we must to deal with the water, the oxygen, and also block the UV degradation. So the barrier property must have this important characteristic, that one of the characteristics are the WVTR, which are the water vapor transmission rate, the OTR, which are the oxygen transmission rate. The WVTR, they can be related with this equation, where the water intake and diffusion inside the membrane are related with these parameters. So we must seek new materials that has low water vapor transmission, and also oxygen, and also reduce the transmission of UV light. So sometimes the combination between polymers and also some layers, for instance, there is some polymers with thin layers of oxides that can be applied to as encapsulators. It's usually one oxide layer over the polymer, but it's important to mention that the encapsulation barrier, they needed to be invisible in the visible light, but block the UV. So if you have some material that has this ability to block the UV but be invisible to visible light, it's nice. And also if they can reduce the water or oxygen intake, it's quite important. Just one for curiosity, here are the applications of organic materials in terms of technology. So for instance, the barrier here are for the water intake. The OLED must have a ultra high barrier because of the degradation. So one small quantity of water or oxygen can reduce degradation. So the barrier performance must be quite higher. Going to OPV, since solar cells or thin film batteries, the barrier can be lower, and working with sensor and also some medical packing, this laminator barrier has lower performance of water intake rate. So in terms of curiosity, here is just for OLED, the water intake is around 10 minus 6. So it's equivalent to one drop across 6 football fields. So if you have 6 football fields of extension, just one drop is the correlation between the number of water that has inside in contact with the organic compound. So when we work with ambient condition, we don't have this it's hard to deal with it because we cannot block the number of oxygen in water. So sometimes it's a deal in terms of scalability and also the encapsulation strategy and stability. So in terms of material, to increase stability, materials with side chains, because of the more stable morphology, or backbone rigidity, so they have this freezing morphology. Even though the extons can induce morphology changes, it will not direct impact because of the freezing morphology. Additives also can work with as stabilizers, or cross-linkers, but it's hard because sometimes the additive can induce the reaction with the oxygen or water, for instance. So it's quite a challenge. As I said, the stability testing protocols to compare different different materials are this one. So we have one protocol for solar cells that has been published a long time, but its application for one sun. We have these ISOs, different for light, dark, and thermal stress. So it's quite important to follow these protocols to improve the reproducibility and also to be also to compare between the laboratories and also to compare between the days of the tests. But one of the biggest issues nowadays are the indoor protocol, because indoor, as you know, we have several characteristics. For instance, we have some lights with one spectra. We have sometimes oscillation in the electrical building and the differences on the electrical, on this light spectra of the lamps. We have also different on the temperature because of the windows open, windows closed, air conditions open or not, and also related to the light spectra. If you have a different distance of your lamp, you have also different light spectra. So it's quite challenging to do one indoor protocol, even though we must seek to compare different strategies to overcome the stability for indoor applications. So just to examine here, it's for OLED, this example, but in terms of degradation, if they are near to the outdoor, they have different degradation. If they are near to the window, so the window has also this low light coming from the sun and also the light from the lamps. So it's quite challenging to overcome this stability issue. So just to review the stability that I discussed, I put it here because of the ETL and HTL can also impact on the stability. Just to help the researchers that are attending this class in terms of self-assembled monolayer or ADBN materials. So the stability of these materials applied is applied in the photoactivity devices. We have to deal with the energy alignment, the selectivity of charge, interface dipole formation, because of the rule of the hole transport layer or electron transport layer. So if you have this located charge at interface, we have these very reactive regions. And if you have these thin layers, we can lose these properties because of the oxygen, electrical field, and ion migration. So depending of material that are used, usually, for instance, P.PSS, as I already talked, spiral or PTAA, or for instance, for ATL, zinc oxide, titanium oxide, PCBN, they have different chemical mechanism of degradations. But for instance, P.PSS, the delamination, the spiral, they can induce doping inside of the active layer because of ion migration from the doped spiral. And the zinc can also be catalytic with oxygen. So it will directly impact on the device's stability. And it's quite important to investigate the material itself that you are developing in terms of stability. So as I said, in terms of ADTL, the P.PSS has this hydrophobicity. The spiral has the dopant migration of the ions in ion diffusion through the from the perovskite through the ITO and ITO corrosion. So to one material to block also this ion diffusion, it's important to overcome this stability related with the interlayers. ETL degradation, also coming from the oxides, zinc card thin oxides, titanium oxide, or in terms of organic interlayer ETL, we have to deal with the aggregation because of the dimers that can be formed with the fullerenes and also the metal diffusions from the electrode to the active layer. So in terms of it, if you will have these side effects coming from the interfaces, even if we seek new material for active layer and the material of the active layer is quite stable, we have these interlayers issues. So sometimes you must analyze your material specifically, even though that different materials can induce different degradation. Knowing your material very well in terms of efficiency, how it works, and how are the stability in terms of temperature, light, oxygen, water, it's quite important to build interfaces and also to improve the stability. The self-assemble monolayer I just put here in terms of what I see in the literature, but it was very fast. I didn't go deep into the self-assemble monolayer. But in terms of stability, they can do defect passivation. So if you have some defect, you can fill this defect with this self-assemble monolayer. You can control the energy level of your surface because of the dipole formation. The dipole formation will be triggered with different morphology. So in terms of self-assemble monolayer, it's quite nice because of this energy level control that they can induce. In terms of bottom layer, you can improve the perovskite growth. So if you improve perovskite growth, it will reduce the charges that are free to move in the perovskite and accumulating the interfaces. However, we have this instabilities mechanism that could be one issue that you could work. For instance, disruption or weak anchoring of the self-assembled monolayer, no uniformity coverage, not in terms of energy alignment, but in terms of process, electrical heterogeneity, and when we move from the lab scale to the large area, the thickness related to the material, the relationship between the thickness and the material. Sometimes in large area, it's not so easy to do thin film. So, and also thin and uniform film. So there is this trade-off on stability because of the film, the ultra-thin film that has good energetic, but in terms of robustness, it's bad. And for 8BN, 8BN seems quite nice material to apply to improve the stability. They have this chemical inert. They can be applied as barrier for ion diffusion. So if you want ion diffusion, you must do some strategies in synthesis, because the 8BN itself, without any anchoring group, maybe they can block the ion, not transport some specific ion. And metal diffusion blocking, because of the metal can induce this diffusion inside of active layer. So 8BN can be a very nice material to block this stability related to the ion from the electrode. So if you want metal ion migration, you must deal, because the 8BN are very stable material to block some molecules and also ions. The stability, the impact on stability is to suppress the ion migration, the protect interfaces, and reduce chemical degradation, because of this ion can accelerate the reactions. Although the limitations of the 8BN are the isolated property, so too thick film, it has this high resistance. Sometimes the interface mismatch because of the thickness, or because of the materials that you are dealing. And also has this integration with large area. It's challenging because of the processing related conditions. So just to take away this part, and going to the last one, the degradation, there is a couple of photophysics, morphology, and chemistry. It's not just to seek new materials, but also to understand the materials that we have. The last topic will be the characterization techniques. So the characterizations are the most important things to observe the materials. So in terms of observation, you have different ways to observe. You can observe with electrical bias, you can observe with light, or you can observe with interaction with two materials. So it's quite nice understand how the characterization works and what are the biggest issue behind the utilization of some characterization, some techniques applied to the organic materials. So the materials, organic materials, as we discussed, they are disordered, multi-phase, and they have this dynamically evolving. So in terms of characterization, they are quite challenged because there is some techniques that you cannot see. There is also some techniques that can induce some artifacts. So maybe you are seeing something that is not there, but you are inducing because of this disordered system. And also because of this dynamically evolving, sometimes the organic that you see now, the stability also it's related to this dynamically evolving, or even the technique itself can modify this property that you are seeing. So the organics are quite challenging this way, and this is the reason that you need this multi-technique approach. So using this multi-technique approach, you can correlate some technique with morphological point of view, electrical point of view, or optical point of view, and bind everything together and see the correlationship between them. So, for instance, here I just put the morphology. So, in terms of the size of the material, if we have thin film morphology around millimeters, you can use optical microscope to see. If you are seeing something with optical microscope, so it's not nice for your application, you must optimize it until you see everything covered. So well covered, well uniformed. If you see with optical microscopy, so you are dealing with things around the micrometer. If you have the well uniformed of your film on the optical microscope, and you must switch to the another kind of microscopies. So there is another techniques, for instance, atomic technique, atomic force microscopy, scanning electron microscopy, transmission electron microscopy, where you can see around the micro, nano, or angstrom. And if you are seeing or you are not seeing anything in these techniques, you must reduce with EPR, for instance, to see the lower scale. So in terms of size of your morphology, you can think that you can start with the large morphology and reduce to the lower scale, because if you start with the lower scale and has some things related with the large scale, there is some oscillation in the morphology that you don't want to see, and it's hard to interpret a small scale. Also here, we have this actually a bit more around an angstrom here, and the molecular simulation would be around angstrom years also. In terms of techniques, I start the discussion with the optical absorption, that are one of the most popular technique in the laboratories. So optical absorption or UVVs, they can measure the electronic transitions. We can use the shape of the spectra to measure the band gap. So the band gap, we can have some insights if the band gap are being modified or not. Also, the UVVs indicate aggregations and also molecular ordering in terms of morphological point of view. So here, for instance, one example, if we decrease the concentration, we have this blue shift in the peak with this same, this is PL, sorry, but I didn't see that it was PL, but we have this, in terms of absorbance here, concentration decrease the number of absorbed, number of the chromophores being absorbing. So we can see in this example here, we don't have any well-defined peak, but if you have this being the last transition of the, you can use the tangent of the lower energy and measure indirectly the band gap of the material. And you have this difference in terms of the concentration, because when we analyze it, when we analyze the transition of optical transition, you have a more freedom or more confined structure. You have different morphology. You created different states, so the material can access this state with different gap. The photoluminescence, the absorbance, it's the absorption of the light, and how is the shape on the UV spectra. The photoluminescence is the energy that goes out of after your absorption, so you can excite your material with light. You created one exton, and this exton moves with diffusion or with resonance transfer, or there is some quenching, I don't know, depending on the system that you analyze. But using photoluminescence, you have several things to interpret it on your material. So you can investigate, for instance, changing if in morphology can induce different diffusion, changing in morphology can induce energy transfer. So there is several techniques, several physical information behind photoluminescence that can help understand how works the organic material. So in terms of it, I can just summarize. We can probe the exton dynamic or the quenching efficiency of the exton creation. And if you analyze a TRPL, that is time-related photoluminescence, we analyze the exton lifetime measurement of the material. So we analyze the intensity in function of the time, and if you have, for instance, nanosecond or millisecond, you are dealing with nanosecond or picosecond, you are dealing with singlet states, or if you have a millisecond or second, you deal with triplets. So there is a lot of information behind photoluminescence. You just needed to focus on the discussion and then interpret the physics behind the photoluminescence. In this way, the optical techniques, they have they do not measure charge, they measure optical signatures, and to interpret the measurement, it's quite indirectly in terms of the charge, because we cannot ensure the charge is moving, but we can correlate using the optical signature of the material. So, for instance, PL quenching could also mean efficient charge transfer or increased non-radiative recombination. So these two both competing in terms of interpretation. So this is the deal using optical technique. Sometimes you cannot see the physical behind because it overlaps with another kind of physics. But you need, for instance, simulation tools or another technique that could help the interpretation of these opticals. Another technique for this is specifically for solar cells are the external quantifications, EQE. So it's the photocurrent related to the wavelength of the energy that are exciting the device. So it gives these spectra, but in terms of charge generation. So we can think that it's one way to combine optical properties with charge. So maybe we can use it to probe the charge transport that we were dealing with the optical measurements. So in this way, for instance, it can give a spectral response in terms of energy related relationship between the energy of the photon with the electrical bias that are generated. But we must have a very well charge collection. So sometimes you misinterpret it because you don't have lower efficiency, but your contact is not very well done. So yeah, it's quite challenging because it's once device fully stacked, and we must have this very well well set up of the devices. And we can correlate with the charge generation efficiency. And for instance, when we combine FTR, the Fourier transform with EQE, we can create this technique that's called the Fourier transform spectroscopy EQE. So you improve the sensibility of the detection in lower wavelength. So for instance, to prove charge transfer states, and you have this technique, it's quite nice to see the energy of this quantum, this charge transfer states. Here is the example of the experiment setup. I'll just go quickly because of the time. So in terms of current voltage, it's the most popular measurement for diodes. So JV curves, these were examples, the application of solar cells. So the solar cells, we measure JV to simulate different resistance in the device. So we can see here, for instance, the conditions for density of current, for short current and open circuit values, and the product of the voltage and the current give us the maximum power point, and the relationship between the VOC, JSC, and the maximum maximum power point. So give us the filling factor, and this is the relationship to see the main parameters for solar cells. I just go quickly here, but you can also through these analyze the traps, for instance, the series resistance here, the shunt resistance here. Also, you can measure without light. So you have the diode factor and also the relationship with the transport using current voltage in terms of frequency of the current. We can also have this Nyquist plot. This one is quite nice to measure, to see the charge accumulation on the interfaces. So this Nyquist plot, they are one simulation with the resistance and capacitive properties of the materials. So the accumulation of the charges give a higher shape of this plot. So sometimes the interface we want to overcome. So we can analyze, for instance, traps using impedance measurements with the current voltage, but with the variation, the frequency of the current. The JV limitation, they don't have this unique interpretation. The same JV can come from the poor mobility of a material, also come from the high recombination, bad contacts. So we must have these complementary techniques to conclude the interpretation. The atomic force microscopy, it's quite important microscopy for organics. I think in terms of size, also the correlationship in terms of the gradation and interaction with the technique, it's the last that can be causing some damage. But through atomic force microscopy, you can see the surface morphology, the roughness, and the phase separation in general. But there is some equipment that you can apply voltage, for instance, and also correlate the difference in the voltage of the tip in your sample, and see how this voltage they conduct in terms of morphology. And there's several setups that could improve the measurements of atomic force microscopy, but in general we use it for surface morphology and see phase separation. There is different modes of the taping, intermittent, or conductivity FN. But there is some information, only the surface we can measure. So this is measurement of the surface because of van der Waals interaction. Cannot probe buried interfaces. Electron microscopy, in general, we have scanning or transmission. Electron microscopy, scanning electron microscopy for organics. The scanning electron microscopy has several important characteristics to observe in the material, but here I just focus on the organics. So in terms, we can see the film morphology of the organics, the thickness if you are seeing the cross-section, or you can have this elementary analysis using the DS. The scanning electron microscopy for organic is if you have a well-covered film, is not so you do not see so many things because of the low phase contract that has with the electron. So in terms of it, we also have a transmission electron microscopy that can observe the nanoscale phase separation. So in terms of phase separation, the nanoscale can be observed using transmission electron microscopy. And also the crystallinity of the organics, but you must have this that is not so common for organics. This technique, you can see, for instance, the charges that you want to analyze for solar cells. Sometimes you see like this, like nothing. It's good because you have a very well film, but yeah, you can not see because of the amorphous structure of the material, and also the sample preparation. It is hard to remove the film from the substrate and put on the grid. So it's quite challenging to overcome this this setup for measurements of the film that are more correlated to the device performance. Kelvin probe or UPS and XPS are here I just put the name of the techniques. I not explain very well, but are the main techniques to measure the work function, and it's very important to construct the devices because of that energy alignment that I talked too much in this class, and also the injection barriers. The GWACs in SACs are also used to see the molecular packing of the organics. It usually measured in the synchrotron facilities, so it's not so easy to measure outside of synchrotron light. In terms of information, we can see the organization of the structures, so maybe correlate fascion, adyon, and also in terms of the distribution in the here, I don't know where I put it. There is, here I just grabbed from the internet. I saw these analytical techniques to measure OLED. So for instance, to prove organic impurities and degradation, there is these techniques, and also luminescence properties, PL, electroluminescence, or for instance, if you want to prove the encapsulation, you can use these analytical techniques here to prove the sealing of the encapsulation. You can also see compositional analysis or distribution of inorganic using these techniques. So there is different techniques to prove the degradation for OLED. General, the OLED also can be correlated for another devices. And the last one is NEXAF. NEXAF is near edge X-ray absorption spectroscopy. So we can probe the electronic structure of the material, and we can analyze the molecular orientation through the electronic border. So you do not see the structure, you see the electronic border, and using this correlationship with the electronic property, you can correlate with the morphology. So we can see, for instance, if they are face-on or edge-on orientation. And here's one example of the measurements and the spectra that we can have if we shift the angle between the measurement and the sample and the light. We have this difference in the spectra, and yeah, you can see where there is higher absorption or not. So the characterization is very well group characterization. So for instance, here, to prove the morphology and performance, we can use AFM, GWAX, and JV curves. So we must need the structure property performance correlationship. So well, this to prove these techniques, we must avoid these misinterpretations that comes not for optical but also the technique. We must understand very well the technique to see the limitations, and also try to use more techniques to avoid the misinterpretation. So yes, this is it. This is the class. I'd like to thank you all for watching and also for coming, and see you.